We will discuss now an algorithm based on interval clocks. So what are interval clocks? So an interval clock, which we call it IC, at a process PI, read at time t, returns a pair. And this pair is an interval. A clock at time t is an interval. So it's an interval like this, where this is t at this point, and this is the lowest part, and this is the highest part of the interval. And this represents an interval in time between the clock value at t dot low to the clock value at t dot high. And the correct time is guaranteed to be in this interval. So the clock value at t dot low is less or equal t, which is less or equal the clock value at t dot high. So this is what we call the interval clock guarantee. So synchronization uncertainty is exposed in the width of the interval. And the longer the interval, it means the higher the uncertainty. And this is the strongest guarantee that can be implemented in practice. So Google data centers have a service called TrueTime, and TrueTime, they implement these interval clocks. So again, which is important to know, that wide interval may hurt the performance of the algorithm using interval clocks, but does not affect the correctness. So this is the way that we want. So the smaller the interval, the better the algorithm. So let's look to the notion of overlapping intervals. If we have a set of clocks, these sets might be each clock on one processor. So the interval values of a set of clock read at the same time are guaranteed to overlap in the correct time. So here we have the first clock. We know that the real time t, or the true time t, is between these two boundaries, the low and high of that clock. But if we have also another clock on another processor at the same time t, so these two intervals overlap. You can see the overlap here. Even if we have a third clock, so these three intervals now overlap, and here is the overlapping period. So this is guaranteed by interval clocks. So let's look to clocks read at different times and see what guarantees we can get. A clock at processor I read at time t1, and a clock at processor J read at time t2, where t1 is less than t2. We know the following, that the lower bound of the first clock is less or equal t, and less or equal the higher bound of the interval clock. And also the same for the second machine. The lower bound at time t2 is less or equal higher bound at time t2 of the interval clock. In such a case, if t1 is less than t2, so this implies that the lower bound of the first clock at time t1 is strictly less than the higher bound at time t2 of the second clock. To see this inequality, you can first see this here in a picture. So this is the picture of the first clock, and this is the picture of the second clock. And we're saying that if t1 is less than t2, then the lower bound of the first clock is less than the higher bound of the second clock at time t2. You can see this, the lower bound at t1 of the first clock is less or equal t1. That is strictly less than t2, which is less or equal than the higher bound of the second clock at T2. We are going to use this invariant or guarantee on interval clock to develop our algorithm for shared memory or linearizable shared memory. So here is the algorithm. We are going to use interval clocks to remove the query phase in write operation. It means that the write operation, which normally takes 2 rounds, one is query phase and the second is update phase. We will try to remove the query phase of the write operation. The read operation works as normal, and you will see that. So we have 2 changes here we have to make. So assume we have a process PI invoking a write operation. In this case, what will be the timestamp of that write operation? Assume now we are at a certain time, we call it T, and here is the current interval of the clock. This is low and this is high. And now the processor wants to assign a timestamp for the write operation. The way it will assign timestamp for the write operation is to assume the worst case and say, okay, here is where my timestamp should be. So we use ci.high to be the timestamp. So this is how you assign a timestamp in the write operation. Now, before an operation, either a read or a write executed by this process PI can return. This is a response of the operation. It has to wait until the timestamp that was assigned to the operation is less than the lower bound of the current interval clock. The timestamp, this is a timestamp associated for the value, and TSO is a timestamp associated with the value that is read or written by operation O. Before you return from the operation, you have to make sure the timestamp of the operation is less than the lower bound of the current clock time. And let us try to understand this by some intuition why this is true. That's what we are going to do in the next slide. Let us build an intuition about why you need to wait before returning from a write operation. We want to wait until we guarantee that operation O1 will return only if we are sure that the next operation will pick a higher timestamp. So here we invoke the write operation O1, and here is our timestamp condition. The timestamp is equal to the upper bound of the interval clock at this point, the clock.high. We perform the operation, so we start the write operation. We collect acknowledgements. So here was the point where we should return, but we don't return at this point. The return will happen later here. Why? Because we have to wait until this condition is satisfied. And what is this condition? It says that at this point, the lower bound of the interval clock has to be higher than the timestamp. And where is the timestamp now? The timestamp will be at this point. This is where the timestamp of operation O1 is. So at this point, the clock lower bound will have a value that surpasses the timestamp. Then we can return the operation. After that, we can invoke another write operation, and we get a new timestamp for this write operation, which is the higher bound of the current interval clock here. So this is fine, and we see why it's fine. What we want to now know is that the timestamp of the second operation O2 should be higher than the timestamp of the first operation. So we can see it here. We know that T1 is less than T2, which would mean, by what we have defined before, the lower bound of the clock at T1 is less than the higher bound of the clock at T2. So we have that. Now, the timestamp is less or equal to the lower bound of the clock at T1, which is strictly less than the higher bound of the clock at T2, and that in turn is equal to that. So everything is fine. The timestamp of O1 is less than the timestamp of O2, and these two operations are ordered in the correct order because operation O1 precedes operation O2. Now we show an example what would happen if the first operation returned early. We'll see that it will violate linearizability. Here is our operation, O1, and this is the interval at the time of the clock, at the time when we invoke this right. So the upper bound is here. It's a very long interval, and the operation should have waited until this point. But it returned early, so it returned here. When it returned here, here is an operation that happens after O1. It's another right operation, and this has a much better accuracy of its interval, so it returned here. So what happens in this case is that the timestamp of the first operation will be greater than the timestamp of the second operation. But this is violates serializability because operation O2 should have happened after operation O1. So if O1 is completed before O2 is invoked, then O1 must be ordered before O2. And this is a case where O1 does not wait and it completes before O2 is issued. So there is no guarantee that O1 is before O2. So here we have seen an example where, in fact, the timestamp of the first operation O1 is greater than the timestamp of the second operation. So this gives an intuition why we need to wait. And of course, if these intervals are small, then the processor might not wait at all. So the better the accuracy of the interval clock, the better that the algorithm will perform. So here is the correctness of the algorithm. The algorithms with interval clock satisfies linearizability. We have two operations, O1 and O2. O1 is before O2, as we can see here. If O1 is a read or a write, and O2 is a read, the same argument as before. O1 is ordered before O2. O2 will just read the timestamp of the write or previous writes. If O1 is a read or a write and O2 is a write, we want to guarantee that O2 will override the value read by O1 or written by O1. O1 is completed at time t, this is this time here, by pi, and O2 is invoked at time t2 by pj. T1 less than T2 implies that the timestamp of the first operation is less or equal the lower bound of the clock of that process at T1, which is strictly less than the higher bound of the clock of the other processor J at T2, which equal to the timestamp of the second operation. Therefore, the timestamp of O1 is less than the timestamp of O2, And since this is the case, the value of O1 is overwritten by the value of O2. This is the pseudocode of the algorithm, and I'm just looking to a single register. So this is the initialization of that register. When you do a read, what do? You say, okay, I am now going to be doing a read. I have a list of acknowledgements that are empty, and I send a read request to all the processes. Each process, when it gets a read, it sends its value and the timestamp. And now, at the requesting process, when it gets a timestamp and a value, it adds it to the read list. When it gets a majority, it picks the maximum value. And if all pairs in the read list are equal, it is going to do this special return, the return that has to wait for a while. Otherwise, it sets an acknowledgement to 0 and do a write. And this write, as you know, it is like the update phase now. We are doing an update phase. So let us look to this do return later. Just now look to the write operation. When you do a write invoke, you set reading to false. And now you set the timestamp to the current value of the clock dot high, the higher upper bound of the clock. You have the no acknowledgement at this point, and you send the write request to all processes. Whenever a process gets the write request, it checks if the timestamp is higher than what it has, then it updates the value. And in both cases, it sends an acknowledgement. When you get an acknowledgement, you increment the acknowledgement, and if you have a majority of acknowledgement, you do the do return. Now we have to focus now about the do return here. This is really what happens. The do return is used both in the write operation and in the read operation. While the timestamp is less than the lower value of the current clock, you wait. Of course, the clock will increase, and eventually the lower bound of the clock will be higher than the timestamp. In this case, you just return the read or the write operation. This ends the lecture on interval clocks or using clocks in distributed system. We have seen two things. We have seen that we can do a better least-based election algorithm, which could be used to do better operation or more efficient operation in a replicated state machine. And we have seen that we can do a better linearizable shared memory algorithm. Better in the sense that the write operation now will take one round trip, and you can wait a little bit longer depending on the accuracy of your interval clocks. And that ends this section.